Greetings, detectives. Mrs. McKay here, and we are working on Clue 5, which is all about using functions in the real world. So let's start by going ahead and filling in our learning target. I can solve linear and exponential functions in, we should write in real world problems. You don't need that in real world problems, okay? And let's just do a quick review. Linear functions, we've learned a lot about linear functions over the year, and you may have even learned about them in your class last year. But exponential functions, they're kind of new. We've just started learning those, so let's compare them a little bit. Linear functions, if you remember correctly, are a straight line, whereas exponential functions are a curve that shoots straight up. Okay? Linear functions are often viewed or seen in different forms, but the one that we're most familiar with is y equals mx plus b, which is slope-intercept form. We use that for graphing a lot. And m represents the slope and b represents the y-intercept. Exponential functions have a form that we've been introduced to, and that is y equals a times b to the x power, where just the b it has the power of x, not the a. And a represents a constant, b represents a constant, and they actually represent important things as we think about what the problem means. So we also have learned that each of these functions have a way that they're changing using a rate of change. And so linear functions have slope, and that represents equal differences over equal intervals. And so that's a steady increase. It just goes up steadily or comes down steadily, but it's very steady. Steady growth, very consistent. Exponential functions, on the other hand, their rate of change is called a change factor, and that means that it's equal factors over equal differences. So when we look at the first term and we want to get to the next term, we actually multiply it by the change factor, whereas in linear functions, we just add or subtract. So exponential functions, actually, this change factor causes them to grow not at a steady rate, but at a rapid rate, okay? So that's just a quick review, and let's go ahead and get down to business. So I've got 3 problems here, and I just want to warn you ahead of time that you might need to take a break because I think this is going to take us a while. All right, Calcurama had a net income of $5 million in 2010, while a small computing company, Computafest, had a net income of $2 million. The management of Calcurama develops a plan for future growth that projects an increase in net income of 0.5 million per year, while the management of Computafest develops a plan aimed at increasing its net income by 15% each year. So let's start by first identifying our key information. We've got 2 companies. We've got Calcurama and we have Computafest. I'm going to do them in different colors so that we can identify the 2. What else do we know? We know that Calcurama has a net income of $5 million in 2010, and that just means the profit that they made. They made $5 million. After they paid all their bills, they had $5 million, okay? And so that was in 2010. We also know that Computafest, in the same year, made $2 million. $2 million. And we know that Calcurama has a plan, and their plan is that every year they want to increase their net income by 0.5 million per year. So $500,000 a year is how they want to increase by $500,000 a year. And then we know that Computafest, their plan is to increase its income by 15% each year. So instead of adding a constant amount, they're going to multiply their income by 15% and add that to it. Okay, so that's our information. Now, let's see if we can create these two companies' incomes using tables. And what we're going to do is we're going to go ahead and think about year 2010 as year 0. That's where we're starting, year 0. So I'm going to start by first creating a quick little table for Calcurama. All right, and I'm going to go ahead and say X is the year, so we'll say that the first year or the starting year was 0, okay? And Y is going to be the amount of money they made. And I'm going to go ahead and write it just like this, 5 million. We know that 5 represents 5 million, okay? And then year 1 would be 2011, and that's going to be 5.5 million, right? Because I added $500,000 to each year. And go ahead and complete this table and see what you do. Go ahead and complete this table and see what you came up with. So I went ahead and went up to year 5, and you should have filled in 6.5, and then 7, and then 7.5. Okay? So that is Calcurama, and that's their income, 5 million in the starting year, 5.5 after the first year, 6 million in the second year, 6.5 million in the third year, 7 million, and so on and so on. And we could just calculate this out forever if we wanted to. Now let's go ahead and do the same thing for ComputerFest. And ComputerFest is going to be a little bit different. And let's go ahead and put X for the years. And Y for the amount of money. And I'm going to go ahead and add in those amounts. But let's start by saying that in year 0, there were $2 million, right? $2 million. And then we're going to need to do year 1, year 2, year 3, and we'll try to go up to year 4. I think we're going to run out of space for writing all of this. So why don't you go ahead and see if you can figure out what the next year would be. What would the next year be? Well, hopefully what you did was you pulled out your calculator and you said $2 million, that's 6 zeros, 1, 2, 3, 4, 5, 6, times 3% equals $60,000. So 2 million, 1, 2, 3, plus 60,000 equals 2,060,000. All right, this is going to get really hard for you to write. I'm terrible at writing tiny, so I'm going to actually type it in, and I'd like you to go ahead then and figure out, you know what? I just realized that I multiplied by 3%, and I really need to be multiplying by 15%, right? Isn't that what it said? So let's do 2 million. Let's do this correctly. 1, 2, 3 times 15% equals 300,000. 300,000. So you can add that to the 2 million and you'll come up with 2,300,000. See if you can figure out what year 2 would be, what year 3 would be, and what year 4 would be by multiplying the previous term by 15% and adding it to the next term. See if you can figure that out. Okay, so I went ahead and erased what I had written and typed it out because I wanted it to be readable for you. So in year 0, they made 2 million. In year 1, 15% of 2 million was 300,000, so I added that to the 2 million and I got 2,300,000. In year 2, I took 15% of the 2,300,000 and I added it and I got 2,645,000. In year 3, 3,041,750. In year 4, 3,498,000 and $12.50. So that is what their two incomes look like as tables, and you can see that by year 4, Computafest is getting pretty close to adding $500,000. They went from 3,041,000 actually to 3,498,000. So if we actually took 3,498,000 and we multiplied that times 1.15, which means we're going to be adding it, the 15%, we would get 4,022,714,375. So now we've already surpassed adding $500,000 to the total. And so you can see that the $500,000 is going to be, the next time it's going to be even more than $500,000. And you could actually work this out and see how much the Computafest will make, because eventually they're going to be making a lot more, I think, than Calcurama. But let's go ahead and continue to look at this, these different functions. So how do these look as recursive functions? So let's think about what a recursive function means. A recursive function means that we're going to take the previous term and do something to it. So as I look at this term, I could say f of x, actually I want to say f of 1, actually I want to say f of 0, f of 0 equals 5, okay, and 5 million, and f of x equals f of x minus 1, meaning the previous term, plus 0.5 million. Do you see how I created that recursive function? I started, I said, where am I starting? I'm saying I'm starting at f of 0. When x is 0, the f of x, or the y, is 5 million. And then to find any term that I want, I have to look at the previous term, f of x minus 1, and add 0.5 million. All right? Let's look at Computafest. Computafest says f of 0 is 2 million, okay, and f of x is equal to the 2 million, okay, we're going to start with the 2 million, oh, sorry, that's not correct either. Let me start again. Let me go release that. I'm trying to do an explicit formula, and I really need to be doing a recursive formula. F of x equals the previous term, f of x minus 1, times 15%, but also the previous term. So if I just wanted to know what the previous term was, if I said that the next term is just what the previous term was, we could then say f of x minus 1 times 1, because that if I just wanted it to be the first term, right? If I just wanted it to be the term before, if I have the 0 term is 2000 and the next term is just the same term, then all I'm doing is multiplying by 1. But it's not just that term. It's that term and a little bit more, 15%. So I'm going to write it like this, 1.15, because I'm multiplying it times the original amount and the 15%. So I'm getting 1 and 15% of the previous term. So that's my recursive. That's my recursive function. So when I'm adding a percentage to the previous term, I have to include the previous term by just multiplying by 1. Does that make sense? All right, let's go ahead and do an explicit function for each of these. So the explicit function for good old Calcurama is pretty simple. Let's see, we're going to say y equals, well, what did I start with? I started with 5 million, so I'm going to write over here 5 million, and this time I'll write it out. And I added to the 5 million, $500,000, which would be $500,000. And I do it how many times? Well, I do it however many years I have, right? In the first year, I add 500,000. In the second year, I add 500,000 plus the previous 500,000, which would be $1 million. So 500,000 times 2. So that's my explicit function. Do you see that Calcurama is linear with an equal difference over equal intervals? It has a constant rate of change or a constant difference, and that makes it a linear function. Let's look at Computafest. Computafest has an exponential function. It's exponential. So how are we going to figure out how much they make? How are we going to write that? Well, let's think about the change factor. Our change factor is actually 1.15, right? Because we're multiplying by the 15%, but adding it to the original total. We're not getting smaller, we're actually getting bigger. So it's 1.15. So that means that our equation would look something like this. Y equals 2 million. So 2 million, that's where we started, right? And each time we're going to multiply 2 million by our change factor, 1.15. And we're going to do it however many times our years are. So in the 0 year, we didn't multiply by 1.15 at all. We just had 2 million. So if I make my exponent be an x, in the 0 year, this would become a 1, because any number to the 0 power is 1. So 1 times 2 million is 2 million. 1.15 to the first power for year 1 would be 1.15 times 2 million, and I'm going to get this 2,300,000. And then the next one, the next exponent would be 2, so it means I'm going to multiply by 1.15, and I'm going to multiply by 1.15 again, and that means I'll get 2,645,000. So that's my explicit function, all right? So which company do you think will make more in the long run? Which company will make more in the long run? Well, why don't you make a guess and give an explanation why? So what did you find out? What I did was I actually started plugging in some numbers, and I found that at 10 years, when I put in 10 years using my two equations, let me pull that up real quick. When I put in 10 years, let's see here, let's use this equation here. Pull it up here. So if x is 10, then that means 0.5 times 10 plus the 5 million. Good old Calcurama at 10 years has made $10 million. So I'm going to go ahead and write when x is 10 years, y is 10 million, okay? And when x is 11, then y is going to be 10.5. And when x is 12, x is going to be 11. And when x is 13, y is going to be 11.5, okay? But let's figure out what happens with Calcurama. So I started with 10 years. So when x is 10, so then I had to pull out my calculator because obviously those are big numbers. And I'm going to multiply 1.15 to the 10th power. So 1.15 x to the y, and I'm going to say it's the 10th power. And that's 4.04555, a bunch of other numbers. And then I'm going to multiply that times 2. And that's basically 8 million. So I'm going to say 8.09 million, okay? So I don't have to do all those big numbers. So I'm going to put 8.09, okay? 8.09. Then in year 11, I could do the same thing, or I'm just going to multiply it times 1.15, because it's just another 1.15, and that gives me 9.30 million. So in year 11, it's 9.30 million is how much Calcurama, or Computafest has made. And then in year 12, I'm going to multiply by 1.15, and I get 10.7 million. Okay, so I'm slowly catching up. 10.7 million. And then let's do year 13. And multiply that times 1.15, and I get 12.3 million. So at year 13, Computafest has made 12.3 million, and Calcurama has made 11.5. And what we'll see, let's go ahead and do one more, 14, and multiply that times 1.15, and I get 14.5 million. So 14.5 million. Oh, let's do one more. Times 1.15, and I get 16.27 million. So at year 15, 16.27 million, whereas good old Calcurama has made 12 million, and then at year 15, 12.5 million. So in the long run, you can see, even though it takes a while, Computafest will in the long run make more money per year if they stick with their model of 15%. Okay? And that moves us on to the magic of compound interest. So this is going to be very similar. Mama Big Bucks puts $20,000 in a bank savings account that pays 3% interest compounded annually. Compounded annually means that at the end of the first year, the bank pays Mama 3% of the 20,000, so they add 600 to the account. Mama leaves her original money, the 20,000, and the interest, 600,000, in the account for a year. At the end of the second year, well, I didn't spell year right there, the bank will pay interest on the entire amount, 20,600. Since the bank is paying interest on a previous interest amount, this is called compound interest. And this is what banks do. It's how that's how people make money. You don't want to have simple interest. Simple interest just says I'll always get 3% of the principal, which was the original amount that I put in. Compound interest says I'm going to add my interest and count that as the amount that I take the percentage on. So let's go ahead and think about a model to represent how much Mama will make after T years. So we can do this several different ways. We could create a table. We could create, and maybe that's what we'll do, is we'll create a table. Maybe we should give Mama a different color. Let's make Mama purple. So, okay, so let's see. X will represent the number of years, T, okay, and Y will represent the amount of money. So in year 0, when she first starts, she has 20,000. And I'm just going to write it like this, 20,000. In year 1, after the first year, she's going to have 20,600. In year 2, she's going to have 15% of 20,600 added to the 20,600. So what's not 15%? 3%. I'm getting all confused with the previous one. 3% of 20,600. What is that? Well, let's try it out. 20,600 times 3% is equal to 618. So 618 onto 20,000 would be 21,218, right? 21,218. And then the third year, we would take 3% of 21,218. 21,218 times 3% is $636, okay? And we're going to add that to, so, plus, that doesn't help me, $636, we won't worry about the change, plus, well, let's try it again. 21,218 plus 636 equals 21,854. And we can continue to do this, okay? So that's a model, and we could then, whatever t was, we could just extend it to find it out. But if we use this model that I've just created, we're going to have to do this 20 times, right? We're going to have to do it 20 times to find out how much she has after her account in 20 years. So what if we used our similar model, or we just, let's see, if we did, we had said that we could take y equals the amount that somebody starts with, right, times our change factor, and our change factor is the 3% plus the other one, so that's going to be 1.03, and we have to put it to the x power. So if x is 20, what's y going to be? Let's see if we can figure it out. 1.03 to the 20th power equals 1.806111 times 20,000 equals 36,000. So it looks like she's going to make $36,122.22. So $36,122 and what did I say? 32 cents? 22 cents. 22 cents. So that's pretty cool. So in 20 years, she will have almost doubled her money. She's going to have made $16,000 in interest, okay, at 3%. So now we're going to talk about creating a formula for calculating compound interest. And this is something that banks use. And it's very similar to what I just wrote over here. Basically, we're going to say A, which is the amount of money in the account after T years. Okay, so however much money we have after the certain number of years, that's going to be equal to the principal, which we're going to have PB. Principal is the original amount of the investment. So that would be the $20,000 that Mama made, or Mama put in the bank. The principal times 1, which represents the previous term, plus R, which is the annual interest rate, to the T power, and T stands for the time in years. So let's look at this one. A equals P times 1 plus R to the T power. And isn't that what I wrote over here? 20,000 is your principal, Y is our A, 1 plus 0.03, which is the interest rate, to the T, which would be the X time power. So that's creating a formula for calculating compound interest. And if we were to graph this, we would see that it would take a while, but eventually it's going to shoot straight up. And the longer Mama has her money in that bank, the more money she's going to make. And that's something that people talk about when they're talking about investing. They talk about the magic of compound interest and the power of time. The longer you keep something in the bank or in an investment, the more money you're going to make over time, because the amount just keeps getting bigger and bigger, and you're taking a percentage, which is much more than just a constant amount. All right, so now let's take a look at depreciation downer, because it doesn't just, compound interest doesn't just work in our favor, it also, or not even compound interest, but just exponential functions, they don't only work in our favor, but they also work against us. And so think about Mama Big Bucks, who buys a car for $20,000, and it depreciates at a rate of 3% per year. At the end of the first year, the car loses 3% of its original value, so it's now worth $19,400. So let's see if we can create a model for Mama's car. Let's see, can we just do a recursive? Could we do a recursive? Could we say that f of t is what we're going to try to find, okay? F of t, and we should probably first tell ourselves that f of 1 is going to be or f of 0 is going to be the first year, and that's equal to 20,000. So I didn't do a very good job, but you can write 20,000 here, 20,000. So f of 0 is 20,000, and f of t is going to be the previous year. So f of t minus 1, the previous year, okay? And we're going to multiply it times a value. Well, if we multiply it by 3%, then that's basically saying that the car is only worth 3% of the previous year. But the car isn't worth 3%. It's actually worth 97% of the previous year, isn't it? Because it's going down in value by 3%. So we could write it like this. We could say times 1 minus the percentage, so we could say 1 minus the percentage of 3%, which is actually 97%, right? Do you see how I got the 97%, 0.97? Because 1, which was the previous year, minus 0.03, okay? So we're basically multiplying the previous year times whatever the previous year is minus the 3%, okay? So that's our little recursive formula. We could have also done a table and written 20,000, take 3% of it and subtract it, and we would have had 19,400. So now we need to figure out how many years is it going to take for Mama's car to be worth less than $500, less than $500. So what if we took our model? Maybe we could create, instead of a recursive model, we could create an explicit equation and say that y, which is the same as f of t, equals, we could even use our same terminology. Maybe we should do that. Let's say the amount or the value of the car is equal to the principal, which was the original amount, right, times 0.97, okay, to the t power. And we could just do a little guessing and checking, couldn't we? Let's start by saying, well, what's the value of the car? What's the value of the car at 5 years? Let's try 5 years. So we're going to take 0.97 to the 5th power. What is that equal to? 0.85. And then I'm going to multiply that times 20,000. And I get that the car is worth 17,174. So that's not too bad. So we probably need to go pretty far. Let's try 0.97 to the 10th power. What is that equal to? All right, that's 0.7. So I'm going to multiply that times 20,000. 1, 2, 3. And I get that it's worth 14,748. So that was 10 years. That's a 10-year-old car. Let's try 0.97. Let's try 20 years. What happens at 20 years? To the 20th power. Okay, and I'm going to multiply that times 20,000. And I get it's now worth 10,000. So it's going to take a long time, isn't it? It's going to take a long time for it to be down to $500. So see if you can figure out how many years it's going to take for it to get down to $500. Well, what did you find out? It took me a while, but I just kept trying different numbers, and I got to 100 years. I took 0.97 to the 100th power, and then I multiplied that times 20,000, and I got that the car was going to be worth $951. So I knew I had to go further, so then I did 0.97 to the 120th year, and that was 0.0258, and when I multiplied that by 20,000, I got that the car was worth 517. So then I tried 121, 0.97 to the 121st power, and I multiplied that by 20,000, and I got 501. So that meant that after 122 years, this car would be worth less than $500, which that's a pretty good depreciation value. The problem is that usually cars depreciate at much greater value, and the older they get, the more they depreciate. So that was sort of a interesting little jaunt there. So after 122 years, or at 122 years, it will be worth less than $500. It actually is like $496. But who keeps a car for 122 years? No one. The car would be totally worthless. Well, those are some real life examples, and you can see that they're not as simple or easy. They don't always come out with nice, clean numbers, but that's what real life is all about. And we can still use these principles, these mathematic principles, to figure things out. It just might take us a little bit of time. And a calculator always helps. So, make sure that you write your key idea down here, and that you kind of think about exponential functions, especially in the real world. Linear functions are pretty easy to identify, but exponential functions, you have to really understand this one, that one right there, the 1 in the 1.15, that represents the previous term because we're adding it on. And if we had done 1 minus 0.03, then that's because we're subtracting it, and that's where we got the 0.97 from when we were figuring out the value of Mama's car. So think through that. Make sure you really understand that, because you want to be able to recognize those kinds of problems when you're working on your cracking the case quizzes, and when you're on the test, and when you're working on your worksheets practicing. I will see you in class.